Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 6. Jacobi Method. The Jacobi method, which is based on orthogonal transformations, is an iterative algorithm used to compute the eigenvalues and eigenvectors of a symmetric matrix. Through a series of orthogonal transformations, the method transforms a symmetric matrix into a diagonal matrix whose elements approach its eigenvalues. The product of all the rotation matrices gives the matrix of eigenvectors. It is particularly useful for small to medium-sized matrices, but is less efficient for large matrices compared to more advanced methods like QR decomposition. The basic Jacobi orthogonal rotation matrix U has the following form. Starts with an identity matrix, that is, the diagonal entries are 1. The matrix is a block diagonal matrix where each off-diagonal block corresponds to a rotation in a 2D plane defined by the coordinates of the corresponding pair of eigenvectors or components. The rotation matrix is orthogonal, meaning that the transpose of U times U gives the identity matrix. For a plane rotation of row P and column Q, C and S denote the cosine and sine of the rotation angle theta. That is why C squared plus S squared equals 1. A plane rotation, using matrix U, modifies only the pth and qth rows and columns of matrix A. The objective is to zero the off-diagonal elements, i.e., make APQ and AQP 0 by a series of transpose U AU orthogonal transformations. With each successive transformation, matrix A is modified until all off-diagonal elements are 0. Accordingly, this orthogonal transformation procedure is expressed as where A sub k plus 1 and A sub k denote the two successive transformation matrices, and A0 equals A. The matrix U is orthogonal, and the triple matrix product transpose U AU alters only the pth row and the qth column elements of matrix A, so we may express this operation as, which gives. Noting that C squared plus S squared is 1, we enforce A prime PQ equals A prime QP equals 0, and also note that C square minus S square equals cosine 2 theta, CS equals 1 over 2 sine 2 theta. From setting A prime QP equals 0, we find. Solving for C and S, we get where alpha and beta are defined as the pth row and the qth column elements of matrix A are modified as a result of an orthogonal transformation. Next, we choose the matrix element APQ, which we want to 0. Having calculated C and S, the new values of A prime PP and A prime QQ can be determined from and APQ and AQP are set to 0. All other elements of matrix A remain unchanged. The eigenvectors are also computed in the same manner, leading to the accuracy of the Jacobi method and its variance depends on the criteria adopted for terminating iterations. The simplest criterion used to terminate the iteration process is to check whether the maximum absolute value of the off-diagonal elements is smaller than a preset convergence tolerance. One must also take into account the relative magnitudes of a PP and a QQ. A suitable criterion involves checking the sum of the squares of the off-diagonal elements at the end of each sweep. The sum of the squares of the off-diagonal elements of the matrix is called the threshold value, which is calculated at the end of every iteration step. To terminate the iteration process, the convergence criterion, defined as the square root of the threshold value divided by the order of the matrix, must be smaller than a tolerance value. The advantages of the Jacobi method are: Jacobi method is simple, reliable, and easy to program. It works well for small to medium-sized, well-conditioned matrices. It gives all eigenvalues and eigenvectors of a real symmetric matrix. The disadvantages of the Jacobi method are: it is limited to symmetric matrices. It converges rather slowly and may require a very large number of iterations. The minimum number of rotations is n times n-1 over 2. The zeros created in previous rotations can be undone in subsequent rotations. Let us consider the following matrix. We want to determine all eigenvalues and eigenvectors using the Jacobi method. We will use epsilon equals 0.5 times 10 to the minus 6 for terminating the iteration process. The first thing we do is look at the matrix and find the largest off-diagonal element in magnitude, i.e., the element that's not on the diagonal but still has a significant value. This element is the one that we want to zero out to make the matrix closer to diagonal, because the diagonal elements of the matrix represent the eigenvalues. Here we observe that minus 10 is the largest off-diagonal element in magnitude. Next, we identify the pair of rows P's and columns Q's are involved with that largest off-diagonal elements, which we find to be the second row, fourth column, and fourth row, second column. These two rows and columns are where the matrix will undergo a rotation. We need one pair. Here, if P equals 2 and Q equals 4. A specific rotation matrix is created for these two rows and columns. This matrix is an orthogonal matrix, meaning it preserves the overall shape and size of the vectors it transforms, and is designed so that the off-diagonal element is made zero. The rotation is done in a way that ensures the matrix stays symmetric, important for preserving eigenvalues. To calculate the cosine and sine of the rotation, first we find the quantities alpha and beta. Then we obtain the rotation cosine and sine as follows. Then we construct the rotation matrix whose second and fourth rows and columns are replaced as follows. The matrix A0 is initially the original matrix. Performing the orthogonal transformation gives the matrix A1. Note that the transformation created zeros at the second row, fourth column, and fourth row, second column. And note that this process modified only the second and fourth rows and the second and fourth columns. The mu value is found to be 2.72718, which means we have to keep iterating. Every time we apply a rotation matrix, we are also modifying the eigenvectors. To update the eigenvectors, we apply the same rotation matrix U to the current eigenvectors stored in the matrix X, which is initialized with the identity matrix I. The transformations will accumulate the eigenvectors, progressively rotating them as we apply more rotations. Here we set the matrix X0, which will column-wise hold the eigenvectors, to the identity matrix, and then apply the rotation matrix U to it from the right-hand side, which leads to the matrix X1. At the second iteration step, we work on matrix A1, and we find the largest off-diagonal element in magnitude to be -7.598,855. They are located at the second row, third column, and the third row, second column. These are the rows and columns that will undergo a rotation. To find the cosine and sine of the rotation, we calculate the quantities alpha and beta as follows. Now we can calculate the rotation cosine and sine values as follows. Then the rotation matrix U is constructed as: applying the orthogonal transformation to matrix A1, we find A2 as follows. The mu value in this step is determined to be 1.95668, which is far from convergence. Next, we apply the current rotation matrix U to matrix X1 obtained in the prior step from the right-hand side, which leads to the matrix X2. At the third step, the rotation operations on matrix and X yield A3 and X3, respectively. The convergence criterion is still too large to stop iteration process. At the fourth step, the rotation leads to A4 and X4. The convergence criterion is still too large. This process is continued. After each rotation, the matrix A gets closer to a diagonal form, and the matrix X, which started as the identity matrix, gets closer to the matrix of eigenvectors. The iteration process is terminated until the convergence criterion is met, that is, the matrix A is sufficiently diagonal. In other words, the off-diagonal elements are small enough to be considered zero, which is monitored by the quantity mu. Note that the mu value becomes less than the epsilon tolerance value after 14 iterations. The transformed matrix A and the eigenvector matrix X after 14 rotations become. After the Jacobi method converges, the diagonal elements of the transformed matrix A are the eigenvalues of the original matrix A. The columns of the transformed matrix X are the eigenvectors associated with the eigenvalues. The order of the eigenvalues in the transformed diagonal matrix A corresponds to the order of the eigenvectors in the columns of the transformed matrix X. We match the column order of an eigenvalue on the diagonal in the transformed matrix A with the column order of the matrix X as depicted. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.